Okay guys, this is our problem for the regenerative cycle. We are having a combination of reheat and regenerative cycle. We have a steam power plant that operates under this condition and generates a net power output of 8 megawatts. Steam enters the high pressure turbine at 10 megapascal and leaves at 550 degrees and leaves at 0.8 megapascal. Some of the steam extracted at this pressure is used to heat the feed water in an open feed water heater. The rest of the steam is reheated to 500 degrees and is expanded in the low pressure turbine to the condenser pressure of 10 kilopascal. So we are asked to show this in a TS diagram, determine the mass flow rate of steam to the boiler and the thermal efficiency of the cycle. So we are going to start just by, as usual, by doing a small diagram of what we have here. So what we have is we're going to start with the boiler. And this boiler will feed a high pressure turbine. We're going to extract paper and pass it through the boiler again. And we're going to expand it in a larger turbine because this is a low pressure turbine. And we go to the condenser. Okay, here what we are going to have is we're going to preheat this water that comes from the condenser with some steam that we're going to extract from the derivation that we make. And we're going to put it in a tank. This tank is the feed water heater. So we need to add a pump in the middle. So what we need to do is this tank is at higher pressure, so we need to put a pump, and then this water, it's the same pressure of extraction. We need to add it to larger pressure. So we're going to add a second pump so we can pump it to the boiler. So let's start numbering our states. This will be 1. The outlet of the pump is 2. The outlet of the feed water heater is 3. Outlet of the pump and entrance to the boiler will be 4. This will be 5, the exit of the boiler, and then this is kind of tricky, this is 6. So condition 6 is the extraction of the high pressure turbine will remain constant. All of this will go back to the boiler. Let me just change this boiler a little bit so it's easier for us to watch. We're going to make this boiler a little bit bigger. So we have the reheat section. Now the gas that we reheat and go back to the turbine is 7, and this will be 8. If we draw it on a TS diagram, we're going to start by a straight line. We're going to start by drawing our dome, and then our cycle. This is the tensor pressure. This will be our extraction pressure. Point 8. This will be our boiler pressure. 8 megapascal. And we have two temperatures. We have 550, and 500. So we know that we extract here, we extract until it gets to this point, then we reheat here, then extract again. We have these two pressures, so we join our lines. So this is 1, saturated liquid, 2, the exit of the pump, 3, 4, 5, 6, 7, and 8. Okay, so we have our first point. Check this diagram. So now we need to solve our problem. So in order to solve it, let's use today green. We know that the efficiency that we have as usual is the network. Let me do this a little bit nicer. So we have the efficiency to be the network divided by Q in, and network we know is the work of the turbine 1 plus work of the turbine 2 minus work of the pump 1 minus work of the pump 2. I'm leaving this because we are going to need multiplier here. And let me just write it now. We can see in this diagram that the amount of mass that leaves this part is y. Well, this is 1 minus y. We need to find out this amount. So we're gonna change this a little bit because we need to count that the amount of mass that this pump is moving is less minus work pump 2. Now the work of the turbine 1 will be, let's add everything. So this will be H5 minus H6 plus 1 minus y because we have less mass flow right there, H7 minus H8. Work of pump 1 will be V1 times the pressure difference. This P2 is the pressure of the tank, which is the same, let's mark here, as the extraction pressure. And the work of pump 2 is the volume of stage 3 times P4 minus P3, and we can say that P2 equals P3. Okay, finally we have to account for the heat, and heat in, just a little bit big, don't worry, is H1, is H5 minus H4 plus Y minus Y, because this portion of the boiler has less mass. We extracted Y to the feed water heater, and we can see that there is our saving. H7 minus H6, because instead of having this full heat addition, we are just multiplying by the fraction of mass that we are heating. We are heating less water. Okay, in the open feed water heater, we can start with an energy balance. And we already did this in the previous video, but we're going to repeat it just for clarity. So we have this balance. This is all the energy goes in, the energy that goes out. Notice that this is the portion of energy that we bleed from the turbine. This is the portion of energy that comes from the feed water that the feed water carries, and this is the whole mass. So solving for Y, we know that this will be H3 minus H2. We do it a bit nicer, just the same way I want in the exam. H3 minus H2 divided by H6 minus H2 again. So with this we can get efficiency, and with the only thing that we are missing is the mass flow rate. But we already know W net, so we know that power is equal to mass flow rate times the specific net work. So solving for mass flow rate, since we know this, so all that we need to do is to compute the properties. We're going to just state what the properties are. I'm not going to find them, each of them, I just show where you find them, but this is a good opportunity for you to try it. I'm going to give you some of the properties and the final results so you know that you are correct. Okay? So let's write properties. So So in here, what we're going to say is, how do we find them? And state 1, we know is saturated liquid. So pressure is 10 kilopascal and quality is equal to 0. With this, we're going to find H1 and V1. You find it in table A5. State 2, we are going to find it by just H1. We're going to adjust the pump work. So H2 will be H1 plus work of the pump 1. And work of the pump 1 is just this. Notice that we are adjusting the fact that the pump is moving less mass here, not here. Okay. So state 3, we know that the pressure is 0.8 megapascal because it's the same pressure that we have in the bleeding of the compressor, and quality is 0, sorry, because we have saturated liquid. So from here we can get H3 and V3. State 4, we have it, we know H4 equals H3 plus work of pump 2. We notice that work of pump 2 we can get with volume 3 plus times the pressure difference. That is why we get V3. So we are halfway. State 5, superheated vapor. So we have pressure of 8 megapascal and temperature of 550 degrees. It is to get H5 and S5. And we're going to need S5 because we are going to assume an asymptotic expansion. So state 6, this is the exit of my turbine, a low pressure turbine. So in this state, we know the pressure is 0.8 megapascal, and the second independent property is that the entropy is constant. So S6 equal S5, and we need to compare it. And what I can tell you is that since Sg at 8 megapascal is less than S6, we still have superheated. So by interpolation, you should get H6 equal to 2812.7 kilojoules per kilogram. State 7, again superheated. You have pressure of 0.8 megapascal and temperature is 500 degrees. So at table A6 you get S7 and H7. We're gonna need this S again, since we are gonna assume that the state 8 is after the expansion. We don't know. We will know that pressure is equal to 10 kilopascal and the Sg is greater than S7. S7 equal S8. So we need to change this. So we know that we have a mixture. We need to compute X and this X is going to be used to compute H8. So for your reference, this quality, it's 0.96, 27. For your reference also, Y should be close to 0.2016, and with it, your final result will be 44.37. Right here, a final solution. Final solution says that the enthalpy is 44.30, enthalpy, the efficiency percent, and the mass flow rate is 54.55 kilograms per second. Okay. So please follow this example, try to do it yourself. You have some of the difficult parts you can do. You have it like the interpolation, and the quality. The rest of the properties are very straightforward, and we already have the solution. So if you don't have the tables, let me just, here are table A5, which you need 10 and 800. Just show it where 10 kilopascal, 400, and for the superheated you need 0.8 and 500, so it's this, actually this two, and for the first superheated is 10 and 550, so it will be this two. Okay, well, thank you very much. Try it. We're gonna solve another problem too, in which we're gonna have more options like reheat, regenerative, isentropic efficiencies, and open and close water feed water, open and close feed water heaters. Okay, guys. Thank you very much. Bye.